So I started by showing how you need to remove the outliers on the 115 microliter dataset. Now it should weigh 0.150 grams. So if you have a look at the mean weight, it's slightly too low. It's 0.149 and it goes from 0.148 to 0.150209. So that confidence interval between the 0.148 and the 0.15029 contains the 0.150, the accurate and correct value. So therefore, the measurements of the students in that particular practical, once you've removed the obvious outliers, are accurate. The pipettes are accurate and they're producing the values that you expect. There's still one that's a touch too high, but anyway, they've got good agreement. Now, having a look at the next one, do you want to look at the weight for the next for 1 milliliter? So go to Analyze, Descriptive Statistics and Explore, change it for 1 milliliter and do the statistics and plots. So let's have a look what happens when we do that. So we've got 0.98, that's definitely a bit short, and the confidence interval goes from 0.96 to 0.99, which does not contain 1, which is the value that it should contain. So not only is there quite a wide distribution of data, so it's not particularly precise, it's also not accurate. But that might be just because of these particular low values. If we go down and have a look, the values that you need to remove are 30, 31 and particularly 38. If we go back and look at the data again, 30 is 0.8910, 31 is 0.8991 and 38 is 0.82. So that means anything that is less than 0.8991, so 0.899 we can put in as missing values for that particular column of data. So we want anything that is as a range with a maximum of 0.8999 and the lowest one might as well set at 0. There are none that low, but that's fine. You can set any value that's lower than the threshold you want because you're just cutting off the bottom part of your data. Press OK. Now we can go back to the Descriptive Statistics, Explore and Analyze again and see whether it's sorted out our data. That's very nicely looking normally distributed data. You look at the significance of the Shapiro, Wilkin, Margraf, Smirnov, they are perfect. There's no reason to suspect it's not normally distributed. Compared to before, it was a long way off being normally distributed, so that's very good. The histogram looks fine, QQ plot looks fine, the scatter in the QQ plot looks fine. You go to the box plot, it's very symmetrical around the interquartile range. The median's in the middle. You've got two slight outliers which are 2 and 20, but they're symmetrical, one above, one below. So everything's looking good for this data set after removing those particular values. However, if I look at the mean, it's still 0.989 and the lower bound of the confidence interval is 0.982 and the upper bound is 0.996. It still doesn't contain the value of 1, which would be an accurate reading. So while this is now a very precise data set and it has normally distributed data, there is still an issue because it is not accurate. This would lead you to go and look at the data and look at how this could have arisen. So this is a systematic problem you've got with the measuring of the data. So if you look actually at the box plot, there's very little of the data that comes up close to having a value of 1. And if you look at the raw data itself, So if I go back to data view, there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of 38 which have 1 in it. This leads you to be suspicious that there's some kind of systematic problem with that particular set of data. It can't be that 1 or 2 people are just misusing the plungers in the pipettes or haven't got very good technique. This is across everybody within the class. You're finding it's underrepresented data above 1. This would suggest that when the calibrations were done, or if the pipettes were all bought from the same company, that company slightly underestimates its values in terms of volumes. So all of the pipettes from that particular company, or all of the pipettes serviced from a particular company, are calibrated in the same way. If they were all calibrated at the same time, they've all been slightly miscalibrated, which is an interesting finding. Not a great finding if you were working on a very rigorous project. It's a small error in accuracy, but these things can accumulate over a large number of experiments. Now we can look at the absorbance data. So again, let's go to descriptive statistics and explore. I'll get rid of the weight ones, put the absorbance, and have a look at the plots on this one. Again, it's not normally distributed. This one's got a long tail out to 2.8. There's all sorts of strange patterns. And if you look, the outliers are 38, 31, and a bit less these others. So 13, 29, 14, and 12. So 38 and 31 we've picked up before. So the same people who had problems with one experiment have got problems with another. This means that you want to go and look at those particular individuals and how they're using their pipettes and using their experimental setup, and perhaps give them more support in doing their experimental work, because there's some consistency and to who's having problems. So if we go back to the data set and we want to look at absorbance, so we want to specify the missing values, and the missing values for the data, I think they need to be above 0.8, going up to 1 or whatever. So if I repeat my descriptive analysis and explore, run it again, has that made any difference? Slight difference on my Kolmogorov-Smirnov and my Shapiro-Wilks. I can see more clearly what's happening in the tail. So actually any values above 0.6 are an issue. So I got rid of 0.38, but I didn't get rid of 31. So actually I want to probably put the boundary for the top end at 0.65 and see if that will get me to where I need to be. So I go back to my data, tweak my absorbance, so down from 0.8 to 0.65. Go OK. Analyze. Descriptive statistics. Explore. Go OK. Now, Kolmogorov and Smirnov is not significantly different. Still got Shapiro-Wilks is significantly different. The problem is this is a slight bulge just beyond the end. It's difficult for you to say that you don't want those, but that would be all the results down to 0.55. Okay, we can move it to 0.55. And see how that does. Right, neither Shapiro-Wilks or Kolmogorov, Smirnov are now significant. There's good fit on the QQ plot. The box plot looks very nice. Indeed, there's these two slight ones here, 12 and 23, but otherwise good. The mean is 0.414. The lower bound is between 0.39 and 0.43, so it's about 0.41. Now the key thing for this absorbance experiment is it should be 10 times the value of the other absorbance experiment. So we need really to look at the other one to know what the two values should be, and to look at their variation, how precise they are. So if this is going to be, need to first look at the 1000, see what happens. Again, Kolmogorov and Smirnov and Shapiro-Wilks are both terrible. This one is because you've got this very big outlier here. So what you want to do in this case is make the difference at 0.15. I think to start with, should, yes, 0.15, actually 0.12 can probably be better to remove all of that, or even 0.11. So let's go back to the data and put some more missing values on here. So it's range of missing values above 0.11 and a high of whatever I want. This is done. Now if we go to analyze, descriptive statistics, explore, go OK. Now I've got something that looks a bit more like a normal distribution. Still not great on Kolmogorov, Smirnov and Shapiro-Wilk. QQ plots are not horrible. You've still got a bit of outliers just because of how narrow, how precise this data set is.